Hello and welcome to another lesson on A-level physics. Today's learning intention is to understand the properties of radiation. The success criteria for today's lesson is to understand how radioactivity was discovered, to describe the properties of alpha, beta and gamma radiation, and to interpret the observations that are made in a cloud chamber. Now, to begin with then, we're going to talk about the discovery of radioactivity, which was actually an accidental discovery by Henry Becquerel in 1896. So, in 1896, Becquerel was actually investigating materials that glow when they're placed in an X-ray beam. He wanted to find out if strong sunlight would also make uranium salts glow as well as X-rays did. He prepared a sample of uranium salts, but typical when you want good weather, there wasn't any good weather to be found, and so he had to abandon his experiment for the day. What Henry Becquerel then did was he placed the uranium salts in his desk drawer, and as you can see on the diagram that we've got there on the board, he placed his uranium salts on top of some photographic film that was wrapped up in paper, and there was also a key on that photographic paper. This at the time probably seemed rather inconsequential because he'd just take them back out when it was the next nice day and do his experiments to see if the uranium salts would glow due to the light then. However, when he actually took the uranium salts out and looked at the photographic plate a couple of days later, what he actually found was he was able to see the key on the photographic film. Obviously, he was quite amazed to see this because he knew that the uranium salts weren't glowing, he hadn't exposed them to light. He realised that the uranium salts must emit radiation which had been able to penetrate the paper and blacken the photographic film that it was wrapped up in. The uranium salts he described then as being radioactive. He then passed the task of investigating this appearing radioactivity to his student Marie Curie. Within a few years, Marie Curie actually discovered other elements that were radioactive as well. One of these was radium, which obviously, turns out to be considerably more radioactive than uranium salts. Now, Henry Becquerel, Marie Curie and Marie's husband Pierre Curie actually shared the 1906 Nobel Prize, and Marie Curie actually went on to get a second one as well for discovering other radioactive elements in 1911. What I've got here on the board, I've just clicked it on a little bit, is actually an image there of the outline of the key that Henry Becquerel saw when he actually did this experiment in 1896 by accident. What you can actually see there is called the Maltese cross, which was a part of the key that he was using. So, with that accidental discovery made, we now know that there are, of course, radioactive elements. Now, then, Ernest Rutherford, who we've talked about already in our lessons on radioactivity, Rutherford wanted to find out what the radiation emitted was when it was emitted by a radioactive substance. So he did several investigations to find out what it was. Initially, he concluded that there were two types of radiation, alpha and beta radiation. He found that the radiation ionised the air, which would make it conduct electricity, and he made a detector which allowed him to be able to measure the radiation and determine how ionising it was. Of the two types of radiation that he found that one of them, alpha radiation, was very ionising, but the other one, beta radiation, was more penetrating than that one. He later went on to find a third type of radiation, which he called gamma radiation, which was even more penetrating than beta radiation. That took him about 12 months. Having discovered those three types of radiation, Rutherford then built on that work to see what would happen to each of the types of radiation when they passed through a magnetic field. The diagram on the board shows the results of this, and the magnetic field in this case being shown by crosses is going into the page. I would like you to now tell me please what you can conclude from these observations using the diagram on the board. Pause the video and write down as much information that you can tell from that picture please. So the first thing that we can see then is of course that alpha particles are deflected by the magnetic field, the beta particles are deflected in the opposite direction, and the gamma radiation is undeflected. It does not have any bearings on it whatsoever. So what you can also see when you look at it a bit more, you can see that the alpha particles are not deflected as much as the beta particles are. Beta particles are deflected much more significantly than the alpha particles. If that's the type of detail you've got in there, great. But if you've already studied Fleming's left-hand rule, either A level or if you can remember it from GCSE, we can pull out a little bit more information than that as well. Let's have a look at the alpha particles. Now, the force on the alpha particle is obviously pointing up the board, so to speak, and the magnetic field, because it's being shown by a cross, is acting into the page. So if we apply Fleming's left-hand rule to this situation, I've just put an animation there on of a hand just to show you, you can see that the second finger, which is current, will be pointing to the right-hand side. And in Fleming's left-hand rule, the second finger of current points in the direction that positive charge would go. So with the force being upwards and the magnetic field being into the page, that means that the positive charge in that instance will be moving to the right-hand side, which the alpha particle is doing. So the alpha particle is positive. Because the beta particle is deflected in the opposite direction, we can see that the beta particle must be negative. Now, Rutherford and scientists still to this day as well use cloud chambers to observe the paths of particles that can cause ionisation. A cloud chamber contains air that is saturated with vapour at a low temperature. When an alpha or a beta particle passes through the chamber, it will leave a visible track due to them ionising the air. Alpha particles always produce straight tracks, which you can see there in the picture that's got the green and yellow on it. The tracks from a given isotope that gives out alpha particles will all be the same length. Beta particles, however, don't produce straight tracks. Remember, beta particles are much smaller and so will be much easier deflected when they collide with other atoms of gas. So what they end up producing are curly tracks instead that have a varying length. They're not as easy to see either as the tracks from alpha particles because the beta particles are less ionising. I haven't got a picture of it on the board there, but if we were to pass gamma through there, gamma we would expect to go in a straight line, but it would be very difficult to see because gamma is the least ionising of the three types of radiation. Okay, now let's consider the wider properties of these because we do need to know about alpha, beta and gamma radiation in considerable detail. Let's talk about alpha radiation first. Alpha particles are made up of 2 protons and 2 neutrons. We now say that the range in air is 0.04 meters typically. However, because the radiation from different sources might be slightly more or slightly less depending on it, we can say that it can travel between 0.03 meters up to 0.07 meters. However, in the exam, it would be best to quote 0.04 meters as being the typical range of an alpha particle. You might have been taught 5 centimeters at GCSE, but that's just a simplification to help you remember it. At A level, we will be expected to say 4 centimeters, typically varying between 3 and 7. In terms of absorption, alpha cannot pass through paper and it cannot pass through thin foil or plastic either. Now, obviously, we've seen that alpha particles are deflected significantly by a magnetic field. Now, there are actually 2 types of beta radiation. We shouldn't really just group them all together. We have beta minus radiation, that is, of course, the electrons, but we can also have beta plus radiation as well, which is a positron. That can normally travel around 40 centimeters in air, but again, depending on the power of the source, it can range from 20 centimeters all the way up to 3 meters. So there's a massive range. In terms of the exam, I would expect you to quote 0.4 meters when asked for a typical range. In terms of absorption, beta can actually pass through paper, but is stopped by 5 millimeters of aluminium. And of course, the magnetic field will deflect beta radiation, but it will deflect it more significantly and in the opposite direction than alpha particles. And then finally, gamma radiation. Gamma radiation is an electromagnetic wave. They are photons of energy that are typically of the order mega electron volts. In terms of their range in air, they follow the inverse square law, which we're going to be looking at in the next online video lesson. But essentially, that just means that as it's travelling along, the energy will be spreading out and becoming less intense. Now, in terms of absorption, it can pass through the most things. It's the most penetrating of the three types, but it is stopped or at least significantly reduced by several centimetres of lead, and it is undeflected in a magnetic field because gamma radiation is uncharged. Now, let's talk about each of these types of emission, because radioactive sources can emit alpha particles, first of all, which is what we'll consider. We've said already that an alpha particle consists of 2 neutrons and 2 protons, and so it is represented by a symbol of an alpha symbol, 4 and 2 in terms of numbers. Now, because we can see that an alpha particle is being given off, the parent nucleus will have its mass number reduced by 4 and its atomic number reduced by 2 to form a new nucleotide. Obviously, the proton number determines what type of nucleus we're looking at. Now, a negative beta particle, which is an electron, is represented by the beta symbol there with 0 at the top and -1 along the bottom. It's got a charge as well of -e, and it's not a neutron or a proton, so we'll find that the A number is unchanged when beta emission takes place. The equation there represents the changes that take place when the nucleus emits a beta particle. In effect, what happens here is that a neutron in a neutron-rich nucleus changes into a proton, which is why the proton number increases. And it also turns into an antineutrino as well, which is what that V bar E is on the end. Please don't forget that when beta particles are given off, an electron antineutrino is also given off. Now, in beta plus emission takes place when we've got a proton-rich nucleus, and what happens in that case is that the proton turns into a neutron and an electron neutrino. So that is what the equation for beta plus emission would look like. Something that we haven't mentioned yet, but it is definitely worth talking about, is that some proton-rich nuclides can capture an inner shell electron, and that causes a proton in the nucleus to change into a neutron with the emission of an electron neutrino at the same time. So that would be the equation that represents electron capture. You can see that we've got the electron being absorbed, and then of course the number of protons goes down because a neutron is being produced. Then finally we've got gamma emission. In gamma emission there is no change occurring in the number of protons or neutrons of the nucleus when it emits a gamma photon. A gamma photon is emitted if the nucleus has got excess energy after it's emitted an alpha or a beta particle. Okay, now we need to talk about the ways in which these particles can be detected. Now, you might hear various types of things get mentioned. You might hear Geiger counters or Geiger tubes or Geiger Muller tubes. They are all a variation on a common theme with how they work. And I've put on the board here for you to see a cross-section of how it works. The Geiger tube is essentially a sealed metal tube that contains a gas at low pressure. The gas can be helium gas, neon gas, or argon gas. There is a thin mica window at the end of the tube that will allow alpha and beta particles to enter the tube. Gamma photons can enter the tube through there as well, of course, but gamma can also get in through the tube walls because obviously gamma is the most penetrating. Now, in terms of the structure of this, you'll see there is a metal rod down the middle of the tube that is at a positive potential, and the tube wall is connected to the negative terminal of a power supply, and it is earthed as well. A key part of this circuit as well is a rate meter or a scale meter that will detect electrical pulses. Now, when a particle such as an alpha particle enters, we know that alpha particles are ionizing. So what happens is that when that enters there, the gas inside the argon gas will become ionized. Now, when that happens, the positive ions are going to be attracted towards the negative electrode, and the electrons that are produced will be attracted towards the central wire, which is the positive electrode. That allows for there to be a flow of current around that circuit where we've got the scale meter. It would only be a brief flow of current, and so we'd get one single electric pulse for each alpha particle that enters here. Now that then gets registered on the scale meter, which gives us the count reading or causes the bleeping that we hear when we do experiments with Geiger tubes. Now, one of the issues that can arise from this type of thing is if the alpha particles come in very quickly after each other. Now, it shouldn't be, for most sources, this wouldn't be too much of an issue, but we do have to take into account there is something called dead time. Dead time is basically the time that it takes for once an ion has been created and caused an electrical pulse to go around the circuit, the time it then takes for those ions to disappear, the current to drop, so that the tube is ready to receive another ionizing particle, whether it be alpha, beta, or of course gamma radiation. Now, that dead time, the time it takes to regain its non-conducting state, basically will be normally around 0.2 milliseconds. That means that if the activity of the source that you are measuring is particularly high, you will be getting a reading that is actually too low. To finish off this lesson, I would like you to have a practice at some multiple choice questions. This is our third lesson to do with radioactivity in the nucleus, so what I would like to do now is show you 8 multiple choice questions. Pause the video on each question, have a go at each one. Obviously some of them will require working out even though they're multiple choice. It's a common myth that you should just be able to spot the answer straight away. After you've had a go at all 8 questions, I will take you through the answers. Okay, so now we've had a go at each of those questions. Obviously, I would have expected you to have paused the video. I wouldn't have expected you to have done it in live time there. Let's go over the answers. So the first one says we've got a lead nucleus that has a diameter of 1.26 times 10 to the minus 14 metres. We were asked, what is the density of a neutron in this nucleus? So let's remember, of course, that density is mass divided by volume. That is our starting point. Now, it's possible to work out both the volume and the mass of this nucleus. We'll start off by doing the volume. We'll assume that the nucleus is spherical. That's an assumption that we're quite happy to make. And the volume of the sphere that is on the formula sheet, if you don't know it, is 4/3 pi multiplied by the radius of the nucleus cubed. We were given in the question the diameter of the nucleus as being 1.26 times 10 to the minus 14. So the radius, therefore, would of course be 6.3 times 10 to the minus 15, which is half of that. Now then, knowing that fact, then it's just a case of substituting that into the equation, 4/3 times pi times that radius cubed, and we'd find that the volume is 1.047 times 10 to the minus 42 metres cubed. Now that we know the volume, it's a case of working out the mass. Well, I know that there are 208 nucleons, and I can times that by the mass of a proton. A proton and a neutron technically have marginally different masses, but for the sake of this question, I'll just use the mass of the proton for both of them, and that comes out as 3.4736 times 10 to the 25 kilograms. Now that we know the mass of this nucleus and its volume, it's just a case of doing density as mass divided by volume. So we do 3.4736 times 10 to the 25 divided by 1.047 times 10 to the minus 42, which gives us 3.3 times 10 to the 17 kilograms per metre cubed. So the correct answer to this question would be option D. Well done if you got that correct. Question 2 said the most accurate determination of the radius of a nucleus is found from. Well, it isn't the distance of closest approach, which we looked at in the first lesson on radioactivity, nor is it the diffraction of low energy electrons. We want them to be high energy electrons, so it is option A. Question 3 said, in the Rutherford scattering experiment, what happened to most of the alpha particles? Well, of course, the vast majority of the alpha particles passed straight through the gold foil without being deflected. So the correct answer is option D. Question 4 says, which graph shows the variation of nuclear density with nucleon number? Well, what you should remember is that the density of a nucleus is actually independent of the mass of the nucleus, because the nucleons will always be the same distance apart. Therefore, the correct answer is option B. Okay, question 5 says P, Q and R are the paths of alpha particles in the Rutherford scattering experiment. All of the alpha particles had the same initial energy and the paths are drawn to the same scale. Which row identifies the order of the paths starting with the smallest distance of closest approach and ending with the greatest distance of closest approach to the target nucleus? Well, if we look at the diagrams, clearly Q has gone closer to the nucleus than any of them, because that is the one that has been deflected the most. Then it would be R, because that has the next most significant deflection, whereas P is going through barely deflected at all. So the correct option would be option B. This is the first question based on the material that we've done in this lesson. It says the count rate from a radioactive source is measured using a Geiger-Müller tube placed very close to the source. The count rate is measured with no absorber between the source and the Geiger-Müller tube. The measurement is then repeated with thin paper and finally with aluminium of thickness 5 mm between the tube and the source. The count rates corrected for the background are shown. And then the question basically says, what types of radiation are emitted by the source? Well, when we've got no absorber present whatsoever, we've got a large count rate of 876 counts per second. When we then go and place thin paper in front of it, we can see that that count rate drops dramatically. Now, because there is a drop in count rate there, that suggests one of the types of radiation is being blocked, and the only type of radiation that is blocked by thin paper would be alpha. So we know that it must be emitting an alpha particle. Then we replace the thin paper with aluminium of thickness 5 mm, and the count rate there has actually gone up, although bear in mind the random nature of radioactive decay, it's basically stayed the same because you'll always get some small fluctuations. Anyway, because of that being the case, aluminium we know would be absorbing beta radiation. So if the stuff that had got through the thin paper was beta, then there would now be a drop in the count rate, which there isn't. So we can tell that we are emitting alpha and we're not emitting beta. There is still some radiation getting through though, which means that the remaining radiation must be gamma. So the correct answer is option B, alpha and gamma only. A similar question from a different year says a detector is placed 20 centimetres from a radioactive source in air. The corrected count rate is 50 counts per second. A 4 mm aluminium absorber is placed between the source and the detector. The corrected count rate then falls to 10 counts per second. The emissions from the source could be, and we need to work out what it could be giving off. Well, because when we place aluminium in the way, the count rate drops dramatically, we know it must definitely be giving out gamma. Okay? Because we're still getting 10 counts per second, that's likely to be much bigger than a background radiation would be. So we were also emitting gamma. And then finally, because it's 20 centimetres away, we know that alpha only typically travels around 4 centimetres in air. So the alpha particles, even if they are being given off, would have been absorbed anyway. So in fact, all three of these types of radiation could potentially be being given off by that source. And then the last question says beta particles are emitted from a radioactive source in the laboratory. What is correct for beta particles? Well, option A says a strong magnetic field will not deflect them. That is not true. A magnetic field will of course deflect beta particles. We mentioned that earlier on in today's lesson. Option B says they're absorbed by aluminium, and again we know that that is actually true, they are. Of course they would damage human tissue because they're ionising and they have a much greater range than alpha particles. They'll typically travel around 0.4 metres, but they can go as far as about 3 metres or so. Okay, I hope you've enjoyed that lesson today, and I will see you in the next online video lesson.